Welcome to Day 5, Geometric Series and Infinite Series. So we're going to work on series again, which is just taking a sum of numbers. Yesterday we were working on arithmetic series, which there's an adding pattern between the terms. Today we're going to work on geometric, where there's a multiplying pattern between these terms that you can see, and going from a sequence to a series means we have terms, and now we're just adding all the terms. So there are three things that we need to know. The number of terms, which is like what we had before. The first term, which is like what we had before. The third thing that we need to know is that constant ratio, the multiplier. Not the last term like we did before. That's for arithmetic. We do not need to know the last term. We need to know the multiplier. What is the ratio between the three terms? So, if you don't know all three things, I could use this guy to help me out. Okay, just like I used the arithmetic sequence equation to help out when I didn't know all three things. Or sometimes you can use this guy and your calculator to figure things out. Sometimes I'd be like, you know what, I don't know how many terms I have, I'm just going to count my enters. So your constant ratio is definitely something you need. If you're not sure what it is, just take a second term divided by the first term, or the third term divided by the second term, and so on and so forth. And that would be the R value. So, sorry, there's no special video to watch. I'm just going to give you the formulas. And here are the formulas right here. The first one, there's two ways to write the formulas. This is one way. I tend to use this one. Okay? Or, if you notice, inside the parentheses, we're just switching the terms inside of the parentheses, and what that does is makes them both opposite, and making them both opposite makes it really the same. There's a reason why we could do it this way, but I don't have to. The big key, though, is parentheses. Make sure you use parentheses. Okay? I might use that special fraction key again, or I may not, but putting parentheses around what we need is very, very, very important. So let's talk about an example. Okay, let's see. The three things I need to know, I'm going to bring it here, are the number of terms. Well, right now the number of terms is, I don't know the number of terms. My first term, I definitely know my first term is 4. And my R, if you don't see the pattern for R, to me the R is times 2 times 2 times 2, so the R is 2. So now I have to figure out the number of terms. One way to do the number of terms is to do using this equation here. So I have 4, 2 to the n minus 1 is equal to 512. I divide by 4 and I get 2 to the n minus 1 is equal to 128. And I have a couple ways to go. I can log it. You know, we've used logarithms before, and I can move the exponent. Or 128 is a nice number. 128 is really 2 to the 7th. So I have 2 to the n minus 1 is equal to 2 to the 7th. The 2's cancel. N minus 1 is equal to 7, or n is equal to 8. So I really have 8 terms. That's one way to figure out that n is 8 terms. Another way is by doing this on the calculator, and I'll show you how. So this is what I mean by using your calculator and counting the enters. This was starting at 4, enter, and a pattern was times 2, enter, and now I have 2 terms. I'm just going to hit enter. I'm going to count until I get to 512. Third term, fourth, fifth, sixth, seventh. The 8th term was 512, so n equals 8 is how many terms I have. So now that I have my 3 pieces of information, I could use this formula in the blue box. My sum of these 8 terms is equal to the first term of 4, 2 to the 8th minus 1 with parentheses around it over 2 minus 1 with parentheses around it. I'm just going to type that in exactly into the calculator, as is. I'm not going to change it. I'm going to just let the calculator do the hard work for me. If you want, you can use that special fraction key. Watch alpha y equals special fraction bar key, 4 parentheses 2 raised to the 8th, get out of the exponent, minus 1, close parentheses, move to the denominator. Now you don't even need parentheses in the denominator, but I'm going to do them anyways. You get 1020, or you could do this without using that key. I could do 4 parentheses 2 raised to the 8th, minus 1, slash or divided by parentheses. This is where parentheses is really important. 2 minus 1. And you see I get the same result. So the sum of those 8 terms is 1020. Let's do this next one. Let's see what I know. Well, let's see. I do know n is equal to 7 because it's given to you. The first term, well, let's plug in 1 to the first term, and I plug in 1. I get 1/2. I think I'm going to use 0.5 just because it's easier to type into the calculator. And my R value, let's see, the first term would be 1/2, the second term would be 1/4, the next term would be 1/8. I think I'm always multiplying by 1/2. So again, I'm going to use 0.5 as my R value. And I get my sum of the 7 terms is equal to 0.5. 0.5 to the 7th minus 1 over parentheses 0.5 minus 1. I'm going to type this into the calculator. As you see, I already typed it in the calculator. I can hit enter. I get this long decimal number. I could do it without that special fraction key. I get the same result. Or, because 0.5 is smaller than that 1, remember I could talk about those two things inside parentheses can switch. I could have done 0.5 parentheses 1 minus 0.5 raised to the 7th. Oops, gotta get out of there. To the 7th divided by, and now I have to do, instead of 0.5 minus 1, I have to do 1 minus 0.5. As long as you switch both things in parentheses, see how they're both in reverse order now, you will get the same result. And there's a final result, and unless I tell you to round, just write all the decimals. I will tell you when you need to round. So let's see how we could apply this to a word problem. So let's say on July 1st of this year, you put $1,000 in an account earning 6%. How much will it be worth in 2032 or 11 years later? I'm using this formula that maybe you've learned in Algebra 2 class, but it's basically the formula you learned this year when we did exponentials. P just stands for the initial principal. A is what you have in the account. So A equals 1,000, 1.06. Why 1.06? Because they're earning 6%. And 11 years later, and I put this in the calculator, and I get 1898.30 is how much I have in the account 11 years later. Let's say the next year you put in another 1,000. So how can we set this up? So A is going to equal to the 1,000, 1.06 to the 11th, plus another 1,000 of 1.06 to the 10th, because now you're going to earn 10 years of interest when you go from 2021, your $1,000, and 2022, your other $1,000. That's going to earn 10 years of interest, and I put both these in the calculator, and I get 3689.15, and that's what I would have if I put $1,000 in the next 2 years into an account. I'm making interest. Let's say we do $1,000 every July 1st in the same account, and I want to see what I have on July 1st of 2032. So my account is going to have $1,000, 1.06 to the 11th from 2021, plus $1,000, 1.06 to the 10th for 2022, plus $1,000, 1.06 to the first for 2031, plus $1,000, 1.06 raised to the 0 for when you put $1,000 in the year 2032. So this is 2021. This is 2022's deposit. This is 2031's deposit. And this is 2032, in other words, that year. And I could type this on the calculator. I could. But I see this is a geometric series because I'm always the amount of money I have each year is being multiplied by 1.06. So what I can do is just use my summation formula. So here are the 3 things I need to know. I need to know the number of times I do it, my initial amounts, and my R, my multiplier. Well, I can see my multiplier every single time I have a 1.06 in there. That's my multiplier. My initial amount is 1,000, that's for sure. And how many times did I do this? Well, you would think it would be 11, but it's not. It is actually just, let's see, we do it from 0 through 11, so counting 0 would be 12. So it is 12 years worth of that I'm putting $1,000 into the bank. So that's a 12 is equal to 1,000. 1.06 to the 12th minus 1, or 1.06 minus 1. I just type this in the calculator. So I put this in the calculator, and I have almost $17,000 in the bank. That means since I made 12 deposits from 2021 to 2032, I put $12,000 into the bank, and at 11 years later, I have about $5,000 in interest earned. So let's look at the last thing, which is called infinite geometric series. That means I have an infinite number of terms, and there's a geometric pattern to the terms. So kind of like these 3, and obviously we go from sequences to series by changing the terms, by adding them. But I think something has to happen special. Okay? So to have an infinite amount of terms, to have a sum, the sequence must converge to 0. In other words, something special needs to happen, and at some point, the last terms that you're adding are equal to 0, or they're so small they're inconsequential, so you keep on adding 0, 0, 0. You're not really adding anything to the series, so we get a final infinite sum. So like I said, something special needs to happen, and we need to converge to 0. That means that last term towards n has to get smaller and smaller and smaller until it approaches 0. It converges to 0. Therefore, my R value has to be less than 1. And it doesn't matter if it's positive or negative, but either way, this is an exponential decay function. And if you think about an exponential decay function, as x goes to infinity, y gets closer and closer to 0, levels off to 0. That's why we have a horizontal asymptote at 0. So what happens if r is smaller than 1, what happens to r to the n as n goes to infinity? So what happens here? Well, let's do an example. Let's do 1/2 raised to infinity. Well, that's an exponential decay function that goes to infinity. Well, if I distribute my exponents, I get 1 over infinity, 1 to the infinity over 2 to infinity. Well, 1 to any power is just 1, and 2 to the infinity is infinity. And I think I've talked about 1 over infinity is equal to 0. So an exponential decay gets closer and closer and closer to 0. So I only need to know 2 things. Why only 2 things? Well, I need to know the first term, I need to know the ratio. Because the other thing was the number of terms. I could not plug in infinity for my exponent. It would never work. But let's talk about why it works. Remember I talked about I could use that other formula. G sub 1 minus r to the n over 1 minus r. Except now we have, since r is less than 1, r to the n is equal to 0. That's what we just did up here. So that means this goes to 0. And when I do all that, this becomes this nice little formula which is only a 2's term in it, and that is my formula for an infinite geometric series that converges to 0. Let's talk about an example. Let's look at this one. You know I'm going to do this one for special reasons. There's my formula right there. Well, let's see. We have 0.9 plus 0.09 plus 0.009 plus 0.00009. Looks like this adds up to 0.9999 going on forever. Let's see my pattern here. There's my first term, 0.9, and every time I multiply, 0.1. 0.1. So my R value is 0.1. If I use this formula here in the blue box, my sum is equal to 0.9 over parentheses 1 minus 0.1, which is equal to 0.9 over 0.9, and that sum is equal to 1. Wow, I think I'm just reconfirming. 0.9999 dot 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 is really equal to 1. For sure. Just did another proof. Okay, let's look at this next one. Here's my first term. And my multiplier here to here is -1/2. So that is smaller than, the absolute value of that is smaller than 1, so I can use my special formula. So I'm going to move this over just a little bit. And I'm going to use my special formula. My sum is equal to 10 over 1 minus -1/2. Parentheses around anything. So, oops. So my sum is equal to 10 over, this is 3 over 2. And I'm pretty sure I learned a long time ago I do not like dividing my fractions. I multiply by the reciprocal. I get my total sum is 20 over 3, 6 2/3 is what I get as the grand total.